Hi, my name is Ben Hardless. Welcome back to the ENM2600 playlist. And today we're going to be looking at ordinary differential equations, just a really simple example that I've taken off the web. I'm just going to work through it so that you can see how it's done. We do have an initial condition given, so we will also solve for the constant that we end up with afterwards. So here it is dy dx is equal to x multiplied by e to the x squared plus 2, all of that divided by 6y squared. The initial condition given is y naught is equal to 1. Okay, so what we need to figure out is this thing actually separable? And so I'll write it a bit bigger here so that you can really see it. So to determine if this differential equation is separable, what we need to do is see if we can get it in the form dy dx, or y prime, however you want to write it, is equal to some function of x multiplied by some function of y. If we can get it into that form, then we are all good and we can separate and integrate. If we cannot, we may have to employ some more advanced methods. So in this case, our f of x is this guy right here, this thing, and our g of y is 1 over 6y squared, right? So that's this guy right here. So we do have the product of a function of x and a function of y, therefore we can say that this differential equation is separable. So that's great. Now what do? What we have to do is get all of the y terms on one side and all of the x terms on the other. So what I'm going to do is multiply both sides by dx, and you should see that these will cancel and you'll end up with a dx on the right. I'm going to multiply both sides by 6y squared, and you should see that this will cancel with this. And now we've got all of the y terms on the left and all of the x terms on the right. So I'll write that out a bit clearer for you because it's looking a little bit crisscrossy over there. So we've got 6y squared dy is equal to x multiplied by e to the x squared plus 2 dx. And that is it. So now what can we do? We've separated the x and the y terms. So the mantra when you're solving these separable differential equations is separate and integrate. So we've separated, now we need to integrate. So we will integrate both sides. We're integrating the left side with respect to y, and we're integrating the right side with respect to x. So let's go ahead and crunch that. So what we're going to get is integral of 6y squared dy is going to be 6y cubed on 3, which is really the 6 on 3 simplifies to 2, so we can just say it is 2y cubed. And now the integral of this business on the right hand side with respect to x, now that's a little bit trickier, so we may have to do some u substitution there. So if we let u equal x squared, then du dx is equal to 2x, which means that dx is equal to 1 on 2x du. So this becomes integral of x times e to the u plus 2 times 1 on 2x du. So now this is pretty cool because what you'll find is that this x cancels with this x, and we are left with integral of 1/2 e to the u plus 1. I've just distributed the half here, so hopefully you can see where I'm going with that. and a du just there. So we can solve that now pretty easily, because we can say now that 2y cubed is equal to, well, the integral of 1/2 e to the u is just going to be 1/2 e to the u. And the integral of 1 du is just going to be u. And then, of course, we would have had a constant of integration from the left side, and we have a constant of integration from the right side. And right now we're just going to add a constant to cover both of them at the end, because you'd end up with a constant minus a constant, and that just is another constant. So we're just putting c here at the end of the integration. It's important to do it here and not later. The reason being that we are then going to have to transpose this to get a solution for y, get this equation in terms of y, and so there's going to be some operations done on the c, and so we need to have added the constant of integration immediately after doing the integrals and not later on. So now we can substitute back in our x squared in wherever we see a u. So this is going to be equal to 1/2 e to the x squared plus x squared plus c. So if we now divide both sides by 2, what we will get is y cubed is equal to 1/4 e to the x squared plus x squared on 2 plus c on 2. Now, where did all of this come from? All I've done is if you look over here where it says 2y cubed, I've multiplied that by 1/2, and so I've multiplied all of this over here by 1/2 as well. And so 1/2 times 1/2 e to the x squared gives 1/4 e to the x squared. The x squared multiplied by 1/2 gives x squared on 2, and the same thing with the c, you get c on 2. So hopefully you can understand how we got here. And of course we can get rid of the cube by raising all of this to the 1/3. So we now have our general solution in terms of y for the differential equation. But remember, we were given an initial condition, which was y of 0 is equal to 1. And what does this mean? This means that when x is equal to 0, because y is a function of x, right? This is y as a function of x is equal to 1 when x is 0. So when x is 0, y is equal to 1. Sorry to say that so many times, but it's just something that people seem to get tripped up on. What we will do is we will substitute in 1 wherever we see a y, and we will substitute in 0 whenever we see an x. And the useful thing about doing this is that we can solve for the value of c. So we can say that 1 is equal to 1/4 e to the 0 squared plus 0 squared on 2 plus c on 2, all of that to the 1/3 power. Now we can get rid of the 1/3 power if we cube both sides. So we cube that and we cube this. Now the 3 on 3 exponent is just raising it to the first power, so we can just ignore that. And 1 cubed is just equal to 1. So this becomes, and I'll move over a little bit, 1 is equal to 1/4 e to the 0 squared. Well, anything to the power of 0 is just 1, so that's 1/4, plus 0 squared on 2 is just 0, so we'll ignore that. And there's still the c on 2. So now we've got something we can work with. Now 1 is just equal to 4 on 4, isn't it? So now we get c on 2 is equal to 4 on 4 minus 1 on 4, which is equal to 3 on 4. Just doing some rearranging there. Now if we multiply both sides by 2, what we will get is these ones cancel out, and we've got 6 on 4, which is the same thing as 3 halves. So we've we found that C is equal to 3/2 for the initial condition y of 0 is equal to 1. Now what we're going to do is we're going to take this value of C and we are going to plug it in up here into our general solution. So what we will then have is a specific solution. So what we have now is y is equal to 1/4 e to the x squared plus x squared on 2 plus c, which is 3/2 divided by 2, so multiplied by 1/2. All of that raised to the 1/3 power. Now 3/2 times 1/2 is just 3/4, so we can just write that as 3/4. And now we have got our specific solution. So just to recap what we did all together, from the beginning, we were given a differential equation and an initial condition. The first thing we did is determine, is this differential equation separable? To determine that, we had to find out if we could get it in the form y prime is equal to a function of x multiplied by a function of y. We figured out that we could do that, and so we decided this differential equation is separable. Then we integrated both sides after getting all of the y terms on the left and all of the x terms on the right. We had to do a little bit of u substitution to get the result, but we got there in the end. Sorry if that was painful for you. I assume you've done it before, and so it was probably a little boring, but it doesn't hurt to revise. So my apologies if you found it dull, but you can always fast forward, I suppose. Then we found a general solution. We just rearranged for y, and we got y as a function of x with a constant of integration still in there. We used our initial condition of y of 0 equals 1 to solve for the constant, and then what we did is we reinserted the constant into the general equation with the value we found to get a specific solution to the differential equation, which is down here. So hopefully you followed everything that we did in that video, and I really hope it's been useful for you. It is a useful tool. There are some cases where the differential equations are not separable, and I'll do a worked example of one of those in the next video. Thanks for your time. Have a great day. See ya.